All right. So let's look at another way of classifying the singularities, and that's using the Laurent series. So proposition, suppose that we have a holomorphic function with a removable singularity. So suppose it's defined in a punctured disk, right? And let's suppose that in this disk we have the Laurent expansion. And so this is minus infinity, right? Again, z minus p to the n. All right. So from this we can actually read off the the type of the singularity that P is, right? So first, if Cn is 0 for all negative n, then P is removable, right? And that follows immediately, right? Because if Cn is 0 for all negative n, then this is just a power series, right? So second, if there exists a k such that Cn is 0 for all n less than minus k, and C minus k is not 0, then P is a pole of order k. All right, and that follows, and the proof of this proposition is left in an exercise, but spill the beans on the proof. It follows just by, if you have only finitely many, well, use the proposition that or the term or whatever we called it, lemma. I don't know what we called it last time. About how to classify poles. So if you can multiply by a power of z minus p, and it's a removable singularity, then it's a pole, right? And you just have to, check that it's really a pole of order k, right? So how about in the third case, maybe if neither of these is true, then that means if Cn is not equal to 0 for all, for infinitely many negative n, then P is essential. Okay. It is an essential singularity, right? So if you can compute the Laurent series, you can you have the classification of the isolated singularity. Of course, that can you can you compute this series is then the trick, right? And again, the proof is basically, so that the hint for the proof is look at this expression, right? It's for both 2 and 3. It's really, the trick is proving 1 and 2 is almost immediate. It's really showing 3 That's at least moderately not trivial. But it's essentially we have all the tools, right? Just show that such a function cannot be a pole, meaning that there is no such L that such that this has a removable singularity, and you know what a removable singularity looks like, right? And you know that the Laurent series is unique, and if F was actually holomorphic in the whole disk, right? If it could extend, that is, through P, if there was a holomorphic function which agreed with F on the function disk, then its power series would just be this series, right? That's really that's the key thing. It's the uniqueness of the Laurent series, and it's the if there is a power series, then that's the Laurent series, right? Okay, now looking at this, we see that it's important to look at the negative coefficients, right? So let's keep this up, and let's give that a name. So this guy is the principal part of F and P, right? So this thing basically classifies the singularity. If it has infinitely many terms, if it really is a series, then it's an essential singularity. If it has finitely many non-zero terms, if it's really just a rational function, right, then the singularity is a pole, and if it is zero, then you're just getting a removable singularity. There really is no principal part. Right, so that's going to be, let's figure out an example. If you write down, let's say, a function like this, I can actually write it down as sort of a power series, except at zero I have to write down it's you think about it, you know why. So maybe actually, if we want that to be the Laurent series, we could look at this, right? So this function has this Laurent series, right? And it's basically just by taking the power series of e to the z, and into one of them plugging in 1 over z, right? And there's going to be the negative ones, and that's where we get this absolute value and factorial. So this, what's the principal part? Well, the principal part is basically this bit of it without the, or maybe this minus this, right? So it's really the principal part. It's infinite. So this thing has an an essential singularity at zero, right? Now, there's actually something more here. Sort of maybe this example sort of hints at that. We can think of, if we let's just do it with let's just start with entire functions. We can think of, we have a function f entire, so f. We can think of infinity as an isolated singularity, right? Because if we really think of C as a subset of the Riemann sphere, then we're just missing at one point, right? We're missing infinity, right? So if we have a holomorphic function here, this has an isolated singularity at infinity, right? Now, that's really the same thing as 1 over z has a singularity at 0, right? Because 1 over z is the thing that takes infinity to 0 and 0 to infinity, right? If I think of it as a linear fraction map, taking the Riemann sphere to the Riemann sphere. So we can classify this isolated singularity at infinity by classifying this isolated singularity, right? And so, for example, e to the z. Well, e to the 1 over z has an essential singularity at 0, so that means e to the z has an essential singularity at infinity, right? And actually, it turns out that every entire function which is not a polynomial has an essential singularity. Well, same thing as before, because you have if I look at 1 over z, I mean, basically I'm just taking that. Let's suppose that I take the power series expansion around 0. We have an entire function. We can expand anywhere. I stick in 1 over z, right? And if that power series has infinitely many terms, right, I'm going to have infinitely many negative coefficients in the Laurent series of this, right? So that means that I'm going to get an essential singularity unless the power series was already finite, meaning it was a polynomial. So we have. So this is an exercise. If or maybe let me call it, if we don't know it's a polynomial yet, let's say f. So an entire polar function is a polynomial if and only if f has a pole at infinity. And actually, it's the order of the pole at infinity is the degree of the polynomial, right? So, for example, let's just do a simple example. If I have the function z, it's a polynomial of degree 1, right? Well, if I want to figure out what's the pole at infinity, well, I just plug in 1 over z into this thing. Well, it's just 1 over z, and look at what sort of singularity it is at 0, and this is a pole of order 1, right? Well, this is a polynomial of degree 1. All right.